discussion.
I'm Ben Bymaster.
Jim Marabasi.
Matthew Bennett.
And we are Team Out of Control.
Hi, you may not know me, but you probably should. Today I'm going to discuss the pollution on our planet Earth. Pollution disproportionately affects the disadvantaged who can't afford to live in areas that are less influenced by the negative consequences. This directly applies to the social justice criteria of reducing imposed risks and harms. These negative consequences can include, but are not limited to, things such as environmental degradation, human health risks, global warming, ozone layer depletion, and infertile land. It is postulated that self-driving cars will reduce idling and increase traffic flow in congested areas because cars can drive closer together at increased speeds, making the most of available roads. A smart grid can be used to ensure this efficiency while removing the risk of human error when cars are operated. A control system is vital to make this possible because a feedback loop can be used with the braking of the car so that the car knows its braking capacity. This is vital because it then can know how close it can drive to the car in front at given speeds to maximize efficiency but prevent cars from hitting each other when stopping. By making vital advances in self-driving electric vehicle technology, those who might otherwise have been most adversely affected by the negative consequences of pollution might otherwise be spared.
The reference input is the position of the vehicle with respect to other vehicles to achieve the desired vehicle separation, and from that amount of force needing to be applied to correct the distance. Our selected plant is the vehicle. Our output signal is a force applied to the brakes of the car. We determined that the minimum distance between cars should be 3 meters at rest. The equation for the minimum distance between cars is a product of travel velocity and the braking deceleration ability. We came to this conclusion using U.S. Department of Transportation and local law enforcement recommendations for minimum distances between cars, along with factoring in human error will be removed. Alright, this is the system we chose and we broke it down. The force represents the force applied onto the brakes. The mass represents our plant, the car itself. Our spring represents the suspension. And over here, the dampers represent the wheels against the ground. We originally wanted to model a positional output based on speed and stopping distance, trying to find the optimal safe distance between cars. What the model lacked was modeling the dynamic force, including dampening and spring from the wheel suspension system. Instead, we modeled the force with respect to time, which could then be used in another model that can control the distance between the cars. This is our circuit representation of our model we showed you earlier. The force is modeled here as a current. Our spring is modeled as 1 over K. Our mass is 1 over ms squared. And our dampener is 1 over Bs. Converting the Laplace transform made it a lot easier to make the transfer function. Our input variables are as follow. For our mass, we chose 2100 kilograms because that's about what the Tesla Model S is currently, which is another example of an electric car. For our spring constant, we chose 50,000 Newton meters because after some research, we determined that was a pretty average spring constant. We looked up the dampening force and we found the equation of 2 times the square root of Km to determine our critical dampening, and then we chose an average percent between 3 and 9 for critical dampening. Using this, we solved dampening constant. Our final transfer function that we determined for position over force ended up being 1 over 2100 over s squared plus 512s over 2100. We then took this and plugged it into MATLAB to design our controller.
So, using MATLAB, we found that the plant is not VBO stable on its own and will need feedback control to provide the stability. The plant dynamics must be fast because traveling at high speeds, the vehicle must be able to process and react quickly to any input. The slowest dynamic in the plant will likely be the brakes because they are what directly stops the vehicle and changes the velocity. Our plant will be affected by disturbances from outside sources, which could include other vehicles, objects on the road, and road conditions. The plant will receive information relating its own position relative to the position of the car in front of it from sonar sensors mounted on the front of the vehicle. It will use this input to make sure that the vehicle can stop in a safe distance. The plant system is not stable, therefore the stability margins are not sufficient to account for the possibility of improperly modeled dynamics. The criteria we used to design our controller system were rise time, the steady state error, and then our social justice criterion was the energy recycling system. For the rise time, we wanted a small rise time, and we chose about 1 second because 1 second allows us to basically, I guess, keep the wheels from squealing while still providing effective braking time. This rise time actually has a direct impact on our social justice criterion because having a faster stopping response time by getting the brakes to that 90% point within 1 second, it means that the vehicle will be able to easily avoid hitting other objects on the road such as people and other vehicles. For the steady state error, we wanted to minimize this as much as possible because decreasing the steady state error means that we're going to get an input, our input into the system is going to closely match our output, which means that we're going to get very little error between what the controller system thinks the vehicle is doing and what the vehicle is actually doing, which increases safety for everybody on the road. Finally, our energy recycling system was chosen as our social justice criteria because we really need to be saving as much energy as possible with these vehicles. By reducing the energy consumption, we can reduce the charging times, which can decrease carbon emissions and really lower global warming. And so the energy recycling system is the same as like what you would see in a typical hybrid vehicle, where when you hit the brakes, you're basically going to turn generators within the wheels and put some of that power from the momentum of the vehicle back into the vehicle's batteries. And by recycling as much of this energy as possible, we're able to, well, again, reduce global warming because we can reduce charge times for the vehicle, and if this were used in a gas-powered vehicle, we would be able to reduce the emissions of that vehicle.
So for our 1 second rise time, the reason we chose that is because we assumed it would be 1 second total from the actual recognition of the threat or the vehicle needing to stop ahead to actually applying the force from the pedal to the master cylinder, taking the fluid, pushing the fluid through the lines, creating a pressure in the caliper to actually slow down the brake rotor. And when the brake rotor starts to slow down, you would have the spring and the dampening from the wheel on the ground, and then the spring compressing through the suspension to hit that 90% rise time and the 90% brake power. We think this all would happen in about 1 second. Another reason 1 second might be a little conservative for this whole system to happen. We chose one system to err on the side of safety to make sure that in a worst case scenario and there was a delay of the actual system to the brake pedal force to the master cylinder, that it would actually still stop the car.
For our feedback loop, we have our initial position is input right here, and it goes out to our C of S function, which we derived from MATLAB as 674.85 times 1 plus 0.69 times S. And that C of S function is really our correction function to try to achieve stability from the transfer function. From there, we go and we have our G of S function, which is the transfer function we derived earlier using the circuit, and we have an output of our braking force. Now, here we have to go and we have to basically feed back the information of what that force is back over here into this part of the block diagram, so that our controller can take the information of both the current position and the input force, and kind of modify our parameters for C of S and G of S to achieve our desired braking force, to achieve our desired stopping time.
So for this first plot that we have here, this shows our step response with a rise time of 1 second. The Nyquist plot that we have here shows our complete feedback control loop, and from this diagram we can see that the loop that we have is unstable because all of the poles are in the right hand side. So after iteration we discovered that the system cannot be made stable with the given specifications. From the social justice perspective though, the rise time result was very good because it gives us that 1 second rise time, and this means that the vehicle will begin stopping quickly, which will reduce the harm to people in the event of having to stop in an emergency braking situation. Because the braking time won't cause the tires to squeal during braking, we can optimize our social justice requirements since energy won't be wasted and can be recycled back into the car's battery. The next plot that we show are from our SciSo tool that we made. This is our root locus plot showing us our two root loci, and then our Bode plots, showing the magnitude, and then our phase diagram. We had a phase margin of about 92.5 degrees, and we never crossed the 180 degrees, so we never had a gain margin. Then from the SciSo plot that we have, our crossover frequency was 2.2 radians per second, which was how we were able to achieve the rise time of 1 second. And then our closed looped Bode plot looks the magnitude plot looks relatively similar, but the phase diagram is a lot different.
After quite a few iterations, we found that we still could not get this model to be stable. We could play with the settings of the vehicle itself, but this is not realistic. The weight of the car, the coefficient of the spring coefficient of the spring and the damping coefficient of the vehicle are all relatively set in stone. We may have estimated them incorrectly, but given the best information we could find, these are realistic parameters. So with that information in mind, the only thing that could be further optimized is the control system itself. The control system is designed to the car. The car is not designed to the control system. Given that information, this model is not realistic and is not stable.